We've come to the last video on SymPy and of course on the scientific computing with Python playlist as we look at calculus with SymPy. So let's see. I mean, we've done a bit of calculus with it already in previous videos, but this focuses seriously on some calculus using symbolic Python. So calculus with SymPy, of course, you already know that SymPy is the symbolic mathematics library for Python. Unlike numerical library, SymPy performs symbolic computation, meaning exact algebraic manipulation, symbolic differentiation, symbolic integration, equation solving, series expansions, differential equations, vector calculus. SymPy is widely used in mathematics, physics, engineering, scientific computing, and of course, education. So of course, after installing SymPy, using pip install SymPy, you can then import it each time you need to use it. And then you can create symbols. Before using variables symbolically, they must be declared. We use X, Y, Z as symbolic variables or any other one you choose. So for instance, you can create a single symbol by just saying X equals SP dot capital S symbol then X in bracket like this in as a string, and then if you call for X now you see this beautiful X coming out. So if you use print, it doesn't come out this beautifully. Then of course you can also have multiple symbols declared like XYZ equals SP dot symbols. So what's the difference? This one, for one, it is capital S and it is not, there's no plural, but many you have small s and it is plural symbols. X with spaces in between XYZ, and then you now have XYZ like that, printed. Then you can then use it for anything you want to use. Then we also have something about symbol assumption. So SymPy allows assumptions such as integer variable. So if you like, maybe you are performing some kind of processes, and you need to very specify that a particular variable is an integer, a particular variable is positive, or a particular variable is real. So you can do that. SymPy allows assumptions such as integer variables, positive variables, real variables. This helps simplify symbolic operations. So for instance, you can say n is sp dot symbol n and it is integer. So any n that is not an integer, you don't want it. Then you can also declare p as a symbol, and p is always positive. So when you're dealing with p, you don't take the negative p into consideration because p is always positive. Then you have symbolic expression. We can construct algebraic expressions symbolically. For example, you can have f of x equals x squared plus 3x plus 2. How do you do that? You have the expression to be x star star 2, that's x squared plus 3x, 3 star x, that's 3x plus 2. So expression x squared plus 3x plus 2. So if you print that, I mean, if you just write the expression, you get x squared plus 3x plus 2. If you print it, it comes out in another form. Like, if you say print expr, it's not as beautiful as when you just call it directly like this. So this one gives you x star star, which is not as good as when you just call the expr on its own, and it looks pretty neat the way it should be. Then, yeah, you can expand expressions, right? We've seen this a couple of times. SymPy can expand polynomial expressions. Example, x plus 1 raised to power 4. So you have the expression x plus 1 raised to power 4. In an expanded form, you have sp dot expand expr. Expanded, now you have x raised to power 4, 4x raised to power 3 plus x raised to power 4 plus 4x raised to power 3 plus cx raised to power 2, 6x raised to power 2 plus 4x plus 1. Then factoring expressions. I mean, we've seen this a couple of times. SymPy can factor algebraic expressions. Example, you have x squared plus 5x plus 6. So you declare the expression. The factored form is then goes by saying sp dot factor of the expression, and it's factored, and you get x plus 2, x plus 3 as required. Then you have simplification. You can SymPy simplify symbolic expressions automatically when possible. Like you have x cubed minus 1. Of course, x cubed minus 1 is x minus 1 into x squared plus x plus 1. Then if you divide by x minus 1 cancels out. So you have x squared plus x plus 1 left. So you declare the expression. The simplified form is got by saying sp dot simplify the expression, and you have simplified form as x squared plus x plus 1 like this. Then you have differentiation. So differentiation computes derivatives symbolically. So example, you have f of x equals x cubed plus 2x squared minus x plus 1. You want to find f prime of x. So here you have f is x star star 3 plus, that's x cubed plus 2x squared minus x plus 1. So to differentiate that, of course, that's going to be 3x squared plus 4x minus 1. So, and the key word here is the diff. So you have sp dot diff. Then you take the function and you take the variables with respect to which you want to differentiate. Now, this is important because you can have other variables. So, for instance, um, Okay, let me do the same thing now, but let me introduce new variables. Like this. Imagine I want to now do, let me say, I want to introduce A, B, X, and then I have SP symbol. Okay, now it's even doing all that. Aha. So it's like this thing is hearing me. Oh. It's hearing what I'm saying. So now it's bringing in, so we now have these functions now. We have ax squared plus bx. So we now want to differentiate that with respect to x. So if we do that now, we are going to get our result in terms of a and b. That's 2ax plus b when we differentiate this. So let's say now, say minus c. Okay. Yeah, let me make this power 3. Let me make this bx power 2. And then I have minus cx, you know, say plus 3, like that. So now I've introduced c, so I have c and this, so I have to include c here. So if you run this now, it's more, we have more terms. So you have 3x squared plus 2bx minus c. So you can actually, so if you have more than one variable, that's why it is good to specify what you are differentiating with respect to. Then 28.8, you have higher order derivative. We can compute second derivatives, third derivatives, higher order derivatives. Example, you have f of x equals x raised to power 4 minus 2x cubed plus 5x squared plus 4x plus 1. Now, already, we are used to having this. So the first derivative we had the other time, like up here, you see that we just have sp.diff f comma x. Once you don't specify the order, that means order one automatically. So here you have sp.diff f comma x for this particular function. So if you do that, you get 4x cubed minus 6x squared plus 10x minus 4. But you want to specify explicitly the order at which you're differentiating. This is important for higher orders, for instance. So here now you have f comma x comma 1. So it means you are differentiating this in one step. So you have f comma x comma 1. So you are differentiating the function f with respect to x first, for one first derivative only. So if you do that, you get the same result, 4x cubed minus 6x squared plus 10x minus 1. So these are two ways of doing the same thing. But this particular way is important to indicate if you want to change the value for higher orders. So for second derivative, now you now have you are differentiating f with respect to x, comma 2. Comma 2 means the second derivative. So that means you differentiate this one again. You differentiate the first derivative again. So that will be 12x squared minus 12x plus 10x. So if you factorize, you get 2 into 6x squared minus 6x plus 5. So if you run this now, this is exactly what you get. So that's the second derivative. These two says second derivative. So if you do this now, here we have third derivative and fourth derivative. So, okay, let me even take this away because I've moved the third derivative to another cell. So if I do this now, we have this. Okay, or better still, let me see if I can take it back to what it was before. Aha. So we can do third and fourth derivatives together. So now I'm calling third and fourth, and it's everything comes together like this. But what if you want to have them separately? So you can just say third separately, and you get 12x minus 12 into 12x minus 1, and then you can also have the fourth derivative called separately, and you get just 24 here. Okay, okay. Um, Let me just call the fourth. Yeah, that'll be 24 now. Yeah, just that. So you can call, if you call them separately, it's neater than when you call everything together. But you can call together too. That's what I was trying to indicate there. Then we have partial derivatives. So partial derivatives happens when you have more than one variable in a function, and sometimes differentiate with respect to a function and then with another. So for multivariable functions like f of x comma y equals x squared y plus sine xy, you can compute partial f, partial x, and partial f, partial y, right? So in this case now you have x comma y, sp symbols x and y now. So you have x squared times y, then sine xy. So fx means partial f, partial x. So you differentiate this with respect to x. So x squared y, that means you're going to have 2xy because y is taken as constant. And here you have xy. So if you differentiate xy with respect to x, you get y. So that will now be y, then differentiate sign, you get cos. That will be y cos xy. So you have 2xy plus y cos xy. That's what happens here when you differentiate with respect to x. And with respect to y, what happens? You have the same function f with respect to y. So when you differentiate x squared y with respect to y, you get x squared Then on this other side, if you differentiate with respect to y, xy with respect to y, you get x. That'll be x sine, I mean x cos xy. And that's exactly what you have, x squared plus x cos xy. Now, there's what we call the partial derivatives, mixed partial derivatives. What this means is that you differentiate with respect to x first, and then you differentiate with respect to y later. So that means that this first one here is differentiated with respect to x. Then you now differentiate it with respect to y. That's your mixed partial fraction. So now this is already differentiated with respect to x. You now differentiate it with respect to y. So 2xy with respect to y, you have 2x plus, if you differentiate it with respect to y, this is now like this is now like chain rule, you know. What is that thing called? Differentiate. This is product rule, yeah, product rule. So you differentiate y, you keep y and you differentiate cos xy with respect to y. So that'll be xy cos xy, and then you now you keep you keep cos xy and differentiate y with respect to y. That'll be cos xy. So if you do all of that together, that's why you get minus xy sine xy plus 2x plus cos xy. Well, that may look somehow, but so let me take the original expression and work it out here. You have f of x cos f of x comma y equals x squared y plus sine x y. That's what we have for that there. So the mixed partial fraction is actually this. You have partial f partial x, which is the same thing as f sub x, right? So differentiate this with respect to x. So if you differentiate with respect to it, that's x squared, that's 2x. So you have 2xy there. Then if you differentiate this with respect to x, differentiate xy first. So with respect to x, you get y. Y comes out here. Differentiate sine x. Sine, you get cos xy. That's the first step in that. So the next step you go for is this now. You have partial squared f, partial x. That was the first step. Then partial y. Now that means fxy. So once you have differentiated it already, you differentiate it with respect to y. So differentiate this with respect to y, you get 2x. Then come in here, now this is a product. So yeah, you can have differentiate, keep y and differentiate this with respect to y. So if you differentiate cos xy with respect to x, xy with respect to y will give you x here. Then if you differentiate cos, you get uh, minus sine xy. That's the first aspect. So this is one term. Plus, now, if you keep cos xy and differentiate y with respect to y will be gone. So differentiate cos xy with respect to y. So that bring x out here. Then times minus sine xy like that. So we can tidy all of this up now. So you have 2x minus xy sine xy, then minus x sine xy again. So that's 2x minus xy sine xy and minus x sine xy. We can, of course, factorize all of that and get something. Uh, okay, what's happening here? I think I've done something. eh, Okay, there's something I should have kept. Okay, for the second part, right? Okay, first time we keep y and we differentiate this. Second one, we keep cos xy. Yeah, we should keep cos xy here. Keep cos xy here. So that here will be just cos. This is cos xy. So xy sine xy minus x cos xy. Then with that 2x now. Yeah, minus x sine xy. Then plus. Okay, because we aren't differentiating that, right? The sign should remain what it was because this is not being differentiated. So we have plus here. Yeah, so minus x sine xy plus 2x plus x cos xy. Nothing is changing with that. So that's what we mean by mixed partial fractions. Differentiate with respect to x and then with respect to y, or differentiate with respect to y and then with respect to x. You get the same result any direction you go. So gradient vector now. So for f of x comma y comma z equals x squared plus 2 x plus x squared plus y squared plus z squared. The gradient is del f. So you have x, y, z, sp symbols, x, y, z. You have this. So the gradient is now going to be sp. So you are going to differentiate over this now. Sp differentiates with f with respect to the variables. For variables in x and y, so you differentiate with respect to x, y, and z. With respect to x, you get 2x. With respect to y, you get 2y. With respect to z, you get 2z because you are differentiating each one like that. So you have 2x, 2y, 2z in that case. Then we have Jacobian matrix. So for vector valued functions, the Jacobian matrix contains all first order partial derivatives. That's what Jacobian function is about. So if you have f1 to be x squared plus y and you have f2 to be sine xy, right? So F now will be SP dot matrix. You can form a matrix of F1 and F2. So the variables now, you also form a matrix of the variables X and Y. So J now is F dot. So this function now, Jacobian of that with respect to the variable. So you have 2x1, y cos xy, x cos y. Well, what that means is this. You have x squared plus y and sine xy, right? So here you have x squared. You have, it's more like you have f1 as x squared plus y, and f2 now is sine xy. So the Jacobian of f1, f2 will simply be partial f1, partial x, partial f1, partial y, then partial f2, partial f2, partial x, partial f2, partial y. That's basically what that is. So to do that now, so the Jacobian of f1, comma f2 will simply be this. f1 with respect to x, differentiate x squared plus y with respect to x, you get 2x. Okay? Then with respect to y, you get 1 there. Then f2 with respect to x. So differentiate xy with respect to it, that's y. So differentiate sine, you get cos. So you have y coming out. So you have y cos xy. On the other hand, partial f2 with respect to y. Differentiate xy with respect to y, you get x. So you then have x, differentiate sine, you get cos, x cos xy. That's the idea of Jacobian right there. And SymPy can do that without blinking. And this is what you have 2x1, y cos xy, x cos xy, like that. Then you have the Hessian matrix. The Hessian matrix contains all second order partial derivatives. It is useful in optimization. It is useful in optimization. So what's happening here is this. If you have x cubed plus xy plus y squared, so h will now be the sp dot Hessian f of f with respect to x and y. So that means second, so you have partial squared, all the second derivatives in short. So this is what Hessian is about. Uh, so you have the Hessian matrix is partial squared f, partial x squared, partial squared f, partial x, partial y, partial y. Then you have partial squared f, partial y, partial x, which, and these two are usually the same. Then partial squared f, partial y squared. That's what the Hessian matrix is. So in that case now, if you then have a function to be, that's what we have there now. This x cubed plus xy plus y squared, x cubed plus xy, x cubed plus xy plus y squared. So to get the Hessian for this now, so h now of f, if you like, is equal to, so first, okay, we get all the second partial derivatives. So we know first of all that this is, let's do this. This is partial f, partial x. That differentiate with respect to x, that's 3x squared plus y. This is 0 here. Then you have partial f partial y. Okay, partial f partial y. That is, this is 0 here. Y here means x, and this is 2y. Okay. Okay, let me even remove this so we can just fix up everything at the end of the day. So with these two now, with this we can then have these different things. So from this we can have partial f, partial x, partial squared f, partial x squared. What you have here, differentiate with respect to x again, that'll be 3x squared, that's 6x. Then you can also have partial squared f, partial x, partial y. So what you have here, differentiate with respect to y, that will be, there's only one y here, that's 1. Then coming over here, you can have partial squared f, partial partial y, partial x. Differentiate this with respect to x again. So there's only x at it, so that's going to be 1. And you can have partial squared f, partial y squared. What you have here, differentiate with respect to y, that's equal to 2. So you can see partial squared f, partial y is the same thing as partial squared f, partial y, partial x. And just like we said the other time, the Hessian matrix with respect to f is simply partial squared f, partial x squared, partial squared f, partial x, partial y, partial squared f, partial y, partial x, partial squared f, partial y squared. So that's simply easy. So partial squared f, partial x squared, that is 6x. partial f partial y, that's 1 here, and this is 1 here, and this is 2 from what we've got. So this is your Hessian matrix like that. So the matrix of all second derivatives. All these are used in optimization, right? The Hessian matrix contains all second order partial derivatives. It is useful in optimization. Okay, so you have the tangent line. So for f of x equals x squared, you can find the tangent line at x equals 1, for instance. So that means you differentiate the expression and you substitute 1. Differentiate x squared to get 2x, put 1, that's 2. That's what we expect to get. So here you have symbol x, f is x squared, f prime, that's you differentiate that. So, and then x naught is 1. So slope, you have f prime substitute x naught for x, and then you have y naught. So at the end of the day, you expand and you get 2x minus 1 as the slope of that line at 1 at x equals 1, right? So we have that for tangent line. Then we have chain rule, right? If you have f of x equals sine x squared, so we have f is sine dot sine x squared. So the f is differentiate that, you get 2x cos x squared. So how is it chain rule in the first place? So f of x sine x squared is what we have. F of x equals sine of x squared. So what we usually do is this. So we say y is equal to sine x squared, and we say let u be equal to x squared. So if u is x squared, that means that du dx is equal to 2x. We keep that. Then now u is x squared, so we now say y is equal to sine u. Okay, this implies that dy du is equal to differentiate sine u, that's cos u. uh so what do we then do? But don't forget that u has something. So u is x squared, so cos u is now cos x squared. So, and what does chain rule tell us? Chain rule says that dy dx here is equal to dy du times du dx. Okay, dy du times du dx. So we put everything together. So dy du is cos x squared, and du dx is what we got for that's 2x. So that everything is now 2x cos x squared. So that's chain rule right there. So SymPy also takes care of that kind of thing. That's why you have 2x cos x squared here. Then there's implicit differentiation. You have x squared plus y squared equals 25. So, and you want to look for dy dx. So implicit differentiation, in this case now you have two variables that you cannot separate explicitly most times. So x squared plus y squared is 25, and we are looking for dy dx. That's what we need. So to get dy dx here, so if you differentiate x squared with respect to uh now you are differentiating y with respect to x, right? So so you can easily differentiate x squared, that is 2x, easy. Now, but if you differentiate y squared, that's a problem, right? So, okay, I think I have a better way of explaining this. Imagine if you have d dx of x squared, that's easy to differentiate. And then you also have d dx of y squared. Now that becomes a problem. And then you also have d dx of 25. So we can see it like this. So this one can go straight. We just have 2x easily. But d dx of y squared doesn't make sense. So you have to now make it like this. d dy of y squared. But because that's not what you are looking for originally, so you have to balance it up with dy dx to balance up the issue so that this cancels out. So you still have your d dx, but then you'd have achieved your purpose in both cases. And this is now d dx of 25 is already 0. So in this case, now you have 2x. So d dy of y squared is now 2y dy dx. So that way you balance things up. So you can then have 2y dy dx equals minus 2x. So if you divide through by 2, you have y dy dx equals minus x. So that dy dx now is equal to minus x over y. And that is what your dy dx is in that case. So minus x over y. And that's exactly what we get when we use implicit, when we do implicit differentiation, if you set it up the proper way. So do the symbol. Y is now a function of x. So you do y as a function of x, not just as a symbol now. X is symbol, y is function. Then the expression is x squared plus y squared minus 25. So you bring the 25 to the right hand side, and then you do implicit sp dot differentiate expression with respect to x. So the solution, you have sp dot solve. So it's more like you're solving an implicit sp differentiate y with respect to x, and then you get minus x over y, just like I got on the other side when I did it manually. Then you have indefinite integrals, right? If you integrate 3x squared with respect to x, you have 3x cubed over 3. So 3 cancels out. So you just have x cubed, in that case, you just have x cubed. Yes. How do you set that up? You do your symbol, declare the function, then do the integral. You have sp dot integrate, and then you have x cubed. Then definite integrals now. So the same, so you have x squared there. So that's 1 over 3 x cubed. So if you substitute from 0 to 2, you get 8 over 3, like you have here. Then you have improper integrals. So here you integrate from 1 to infinity. And by the time you do all that, you remember infinity is 0, 0, oh, oh, like that for in SymPy. So the answer is 1. Then you have double integral. So for double integrals, I think in one of the previous videos, not this playlist now, I've talked about double integral. So you integrate with respect to x first, and you do with respect to y, and the answer ends up giving you 3. So once you just set it up this way, and then you have limits now, sine x over x. We've done that also in a previous video under this playlist. So from L'Hopital's review, substitute. The first thing you do with limit is you substitute directly. But if you substitute directly and it doesn't work, then you have to now you have to use other methods like L'Hopital's to sine x, differentiate to get cos x, differentiate you get 1. Put 0 now, cos 0 is 1. So that's why, though at first sight, it looks like sine x by x has no limits as x approaches 0. But if you do other things, you get that it approaches 1. For one-sided limits like this, you can have the expression is 1 over x. So you are saying as x approaches 0 from left and right, negative and positive, everything is infinite like that. Then you have Taylor series. Sin x can be expanded around x equals 0 in Taylor series. And we saw this in the last video also. So you just set it up sp dot series, sp sin x from x equals 0 to 10. So this 10 tells you the order of error you want. So you can change the order of error to say, if you change it to like 12, so it means you're going to have these expressions up to the 11th, up to power 11, like that. So that's so powerful. Then solving equations, like this kind of equation, we've seen it before. So you just use your normal solve, you get -2 and 2. We saw it in the last video, I think, when we're focusing on solving equations. For a system like x plus 3, y minus 3, x minus y minus 1, solving for x and y, you get 2 and 1 in this case. Then you can also do critical points. Critical points means differentiate to get 3x squared minus 6x, and you equate to 0, so you're going to get 0 and 2 here. So equate to 0 and solve for x. So 0 and 2 are like critical points here, or what you call points of equilibrium in some situations, depending on what you're working at. Then find the minimum of this. So again, f of x equals minus x squared plus 4x. You find a critical point. So you have minus 2x plus 4 equate to 0, and you get your value, you get the critical value for x to be 2. If you substitute 2 here, you get 5. So the maximum of this now will be that 2, 5. And this is how you set it up. You declare your symbol x, you declare the function f, you have the prime, then you get the critical value, and then you have all of this going. So we have this. Then you can have differential equations, dy dx. So we've always done dy dx equals y, where we know that that's a c1 e raised power x, but I just made it y squared now to make it a bit different. So you declare x as symbol, don't forget, and you declare y as function, because when you solve a differential equation, you're going to get a family of functions. So y is function. So the ODE now is sp equation yx dot differentiate derivative like this is how you write the y dx here. Yx dot diff x, then yx squared. Then you solve that and you get y of x equals minus 1 over c1 plus x, like that. Okay, then you have second order differential equations where you have d squared y dx squared. Of course, this one now you can do so this is like m squared minus r, and then you get some values, and then you can have c1 e raised power minus x, c2 e raised power x, because when you solve m squared minus say 1 now, so, m squared minus that's m minus 1, m plus 1. So you get 1 and minus 1. That's why you have this minus x and plus x here. So you can check the videos on differential equations if you want more details about solving differential equations. Laplace transform. I have a playlist on Laplace too if you want to take care of that. So you have f of t equals sine t. So, and then t sub s, you declare the symbols. F is now sine t. So the sp dot Laplace underscore transform of ft this. So you do that and you get 1 over s squared plus 1. And I think that's the usual thing for sine. Then inverse Laplace transform. So you like you're taking back what you started with. So you have sine t, you take it back to where it came from. And then you have the plotting. SymPy includes symbolic plotting tools. So from SymPy dot plotting, so I think we did this in a previous video also. So you want to plot x squared minus 2. And this is exactly what you have here. So you can also lambdify. So lambdify converts symbolic expressions into fast numerical functions. So we've also done this in the previous video. You want to check. So import NumPy, you have the symbol x. So expression sign x plus x squared. So you turn it into an expression where you can, using NumPy now, NumPy deals with arrays. You now want to evaluate that function at 0, 1, and 2. So you get the values like this. Then you have, then you can have a set of things under NumPy now. So you have uh you get NumPy, you get SymPy, Matplotlib, you have variable x, expression is signed x to lambdify. Now you have x express NumPy at minus 10, 10, and 50. Then you have y to be a function of x now, of this now. Then if you plot, you get this kind of plot we have down here. So here you're combining NumPy and Matplotlib to get this kind of sign function. So in summary, in this lesson, we learned symbolic algebra, differentiation, integration, limits, series expansions, differential equations, vector calculus, plotting, numerical evaluation. SymPy is one of the most powerful symbolic mathematics libraries in Python. So we have practice problems. Now differentiate f of x equals x raised to 5 minus this. I mean, you have 1, 2, 3 here. Then you have 4 and 5. Compute the partial derivatives. Then problem 5, find the gradient vector. You have all of these examples done. So you want to just refer to the code and just modify the codes. Problem 6, 7, 8 here. Then you have 9, 10, and 11. Problems 9, 10, 11. So e raised by x up to degree 6. Then problem 12, 12, 13, 14 here. 12, 13, 14. Then 15, 16, and 17, and 18, 19, and 20. All right, so with this, we come to the end of the SymPy library and the end of what we call the scientific computing with Python. So after this, like I promised, I'm going to be talking about some special functions like we saw under the SciPy.special, like all these gamma function, beta function. So watch out for that playlist. Let me know how helpful this is for you. If there's something else you have in the trial, feel very free to let me know. If you have subscribed to this channel already, I thank you so much for that. If you haven't, what exactly are you waiting for? Why not subscribe right now and hit the notification bell so you can always get alerted each time a new video is released. You can also become a member of this channel and get some special perks. Some perks, when you click on join. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing math right. Bye.